my name is Iris. Thank you for joining me. I will be talking about revisiting thermal models of subduction zones. So let's have a look at some subduction zones. In subduction zones, you have a lot of earthquakes and a lot of different types of seismicity at that. So you have the more shallow, more conventional, if you want, earthquakes that occur on the megathrust and shallow faults, such as splay faults and outrise faults. And then if you go deeper into the slab, you also have intermediate depth seismicity at depths of 75 to 300 kilometers. And if you go even deeper, you have deep earthquakes at depths larger than 300 kilometers. Now, all these types of seismicity depend on the thermal structure of subduction zones to an extent. For example, in the case of megathrust earthquakes, the seismogenic down dip limit depends on the 350 to 450 degrees Celsius isotherm. Beyond that, you have a ductile regime, and the mechanism causing these earthquakes doesn't really occur anymore. In the case of intermediate depth seismicity, people have hypothesized that they occur due to dehydration reactions, which again depend on the temperature and pressure at depth in the slab. So if we want to understand seismicity in subduction zones, and we do because they pose a significant hazard to society, we should investigate the thermal structure of subduction zones. And of course, people have thought of this, so they have done this. One very famous paper is by Syracuse in 2010, where they made lots of different models of different regions on Earth. Here I show an example of central Honshu in Japan. And they modeled the thermal structure of the slab, which has given very useful insights and information. However, as all models and all modeling studies, they made certain assumptions and simplifications. And one of these assumptions was that they use constant thermal parameters. So think about thermal conductivity, heat capacity, and density. They assumed constant values, which is a fine assumption, unless you think about what actually happens in the lab, because it has been shown that these kinds of parameters actually depend on temperature. Now, you might think this does not make that much of a difference to the thermal structure of subduction zones, and you might be right, but you might also not be right, because we don't really know. And if we want to advance our knowledge of the thermal structure of subduction zones, we think that taking into account these temperature-dependent thermal parameters is something we should at least look at. So that is what we are going to do in this talk. We are going to look at the effect of temperature-dependent thermal parameters in very simplified subduction setups. Why do we simplify the setup? Well, we want to study the effect of one thing, namely the temperature-dependent thermal parameters. So if we have a setup that is completely constrained, that is our best scenario for doing it. So in order to get this very constrained setup, we are looking at the Van Keken and others community benchmark from 2008. As you can see, this is a model setup. It's very simplified. We have a subducting slab here that is going downwards with a fixed velocity of 5 centimeters per year. And we have a rigid overriding plate. And then here in the corner, the wedge, we compute the velocity field. And this whole model can have different rheologies. It can be isoviscous, olivine diffusion creep, and olivine dislocation creep. Those were the cases that were discussed in this Van Keken paper. We also have temperature boundary conditions, which of course are very important if you want to look at the thermal structure. So we have a fixed temperature at the top, outflow for the heat equation, a linear gradient here. And at the left boundary, we have the half-space cooling model that defines the thermal structure of the slab. Now what we are going to do is we are going to run these models based on what Van Keken has done before, and we are then going to add temperature-dependent thermal parameters. And because the half-space cooling model is typically calculated with constant values for these thermal parameters as well, we are also going to change this left boundary to a more complex plate model and then include these temperature-dependent thermal parameters there as well. Okay, so what are we going to do exactly? First of all, the temperature-dependent thermal parameters. Here you can see what Van Keken used in his model, so constant values in orange. And what we are going to use is this pink line, which is based on Mackenzie and others 2005, where they presented a parameterization and approximation of the findings and lab experiments of Hofmeister in 1999. Then, that was for the thermal conductivity. Now onto the heat capacity. We have this pink curve here, which is based on Berman and Aranovich in 1996. And then for the density, we use this pink curve here, which is a very common temperature-dependent density based on Bohicht in 1996. Then, as I told you, Van Keken uses the half-space cooling model for the left boundary of the model. So this is what the half-space cooling model looks like. So here we have the depth, so this is the surface, and then the lithosphere with depth, and then the age of the plate. And we are going to consider a 50 million year old plate because that is what happened in the Van Keken benchmark. And that means that as the left boundary condition, we take this 1D profile through here at 50 million years. But we are also going to look at a more complex plate model, and that looks like this. So you can see the difference. And then we are going to take 50 million years for that. And initially we do it with constant thermal parameters by Van Keken again. But in order to be consistent later with when we have temperature dependent thermal parameters, we then add those, and then it looks like this. So you can see the difference here again. Great. So now we know what extras we are going to add, and we can have a look at some of the results. So I will show you the results for diffusion creep and dislocation creep, and we will start with diffusion creep. So what I will show you in this panel is always the model as Van Keken presented it in 2008 with temperature. You can see it here in color. And I always plot the 400 degrees Celsius, 800 degrees Celsius, and 1200 degrees Celsius isotherms so that you can see the thermal structure a bit better. So this is what it looks like for diffusion creep rheology with constant parameters and a half-space cooling model. And then if we add temperature-dependent thermal parameters, so our model, it looks like this. And immediately you can see that there are some changes. For example, the isotherm is much deeper here. But it can be very difficult to compare this just side by side. So I am showing you a panel here where we show the temperature difference. And this is always the middle panel minus the original Van Keken benchmark. So what we see here is that the differences are quite dominated by this blue blob here, which is the differences in the overriding plate and the wedge to an extent. But this is not what we are interested in. We are interested in what happens in the slab because those dehydration reactions for intermediate depth seismicity occur in the slab. So that is what we're going to look at today. So we are going to kind of blur out our wedge and overriding plate. We're not interested in that. And we're going to change the color bar a little bit so that we can see what actually happens. And in these difference plots, I will always plot the 20 and minus 20 contours to again highlight the structure a bit more. Now, what can we see? If we add temperature-dependent thermal parameters, we get a cooler top of the slab and a warmer slab at depth. And we can also see what happens when we have this different left boundary. So this is what you see here. Here we have the Oceanic plate model, and you can see the only difference really is that the bottom of the slab is slightly hotter. Now, if we combine these two, so we have both temperature-dependent thermal parameters and an Oceanic plate model, we see the following, and we see quite big differences compared to our original model. Namely, we see that the top of the slab is a lot colder and the bottom of the slab is a lot warmer. And these changes in temperature are up to 65 degrees Celsius. So we can look at the same things for the dislocation creep model. And here again, we have the model presented by Van Keken in 2008. And then we add our temperature dependent parameters. Again, we see the isotherm depths changing. And then if we look at the temperature difference, again, it is very dominated by this blue block here. We're not necessarily interested in that at the moment. So we're going to ignore that and highlight what happens in the slab. And we see again that the top of the slab is colder and the bottom of the slab is a bit warmer. We again see something similar if we look at the left boundary. So if we have our oceanic plate model instead of the half-space cooling model, we see that it's much hotter at the bottom of the slab. And combining these two effects, but now for dislocation creep, we see something very similar as for diffusion creep, namely the top of the slab is much colder and the bottom of the slab is much hotter. So I just want to wrap this up and provide you with a little bit of a summary of what I've shown you today. We have investigated the effect of temperature-dependent thermal parameters on the thermal structure of the slab in a very simplified subduction zone setting so that we could isolate that effect. Then we've also tested the effect of using a more complex plate model instead of the half-space cooling model used by Van Keken. And we find that these differences in slab temperatures can differ by up to 65 degrees. And this is quite a lot if you take into account that the down-dip limit of the seismogenic zone, for example, is dictated by the 350 to 450 isotherm. 65 degrees difference is quite a lot. Due to these different temperatures, the depths of the isotherms, of course, also change. And to give you an idea of how much they change, kind of quantitatively, here are some numbers. So the 350 degree isotherm changes by 4 kilometer depth, and the 600 degree Celsius isotherm changes by 30 kilometer depth when you add both the complex plate model on the left and the temperature-dependent thermal parameters. And the distance of how much it changes for a certain isotherm becomes increasingly large for larger isotherms. And these things are, of course, very important when considering seismicity. It affects the location of dehydration reactions, and it has effects for intermediate depth seismicity. And our idea with this project is now that we kind of know this, we would like to build upon this and start applying it to different regions in the Earth as well, and then compare it eventually to this intermediate depth seismicity. That is our goal. So thank you very much for joining me, and I hope you have a great day. Thank you. Bye.